Hello there. Inferences about population central values. Okay, so here we are looking at our first crack at statistical inference. And if you recall, statistical inference is a process of making judgments about a population based on properties of a sample drawn from that population. Now, we have two ways to do statistical inference. The first way is estimation, and it involves I'm going to put in here guessing or approximating. I don't really like the use of either one of those, but the sense that there's a parameter that's unknown and we want to say something about it. We want to guess at its value or approximate its value. We want to estimate its value. The other approach is through hypothesis testing, and it involves choosing between two opposing statements concerning a parameter. And so these are the two main methods to do statistical inference for us, and really for most statisticians. We're going to first look at estimation, and then we're going to look at hypothesis testing. So for a while we will be looking at estimation. Estimation has many practical applications. Here's some examples. A manufacturer of a washing machine might be interested in estimating the proportion of washers that would fail prior to the expiration date. Okay, so when you look at this statement here, you can identify what the parameter of interest is. It's that proportion there, pi, and the manufacturer would like to know something about that, because if the manufacturer knew something about that, then the length of warranties that they would sell they could have a better sense of how long they should be and how much they should charge for the warranty and this sort of thing. Another example is a physician might wish to estimate the mean waiting time of his patients. Okay, and so here we're trying to estimate a population mean mu. Now, unless the physician is able to look at all of his waiting times, all of his patients' records, mu is unknown, so he tries to estimate that. So the first way that we look at estimating is through what's called a point estimate. Let's motivate that a little bit. Suppose we ask 100 SFA students how much money they spent on textbooks for this semester, and we get a sample mean. So we have 100 data points, and we compute a sample mean that is an X bar, and we get 382.25. Well, this value, again, is the sample mean. It's a statistic. It's not the parameter. But if we make a claim like this, that SFA students spend on average $382.25 on textbook purchases for the semester, maybe you see that on a flyer, this sort of thing, then we are using the sample mean as an estimate, a point estimate for the population mean. Now, in this setting here, we're using the sample mean, yes, as a point estimate for the population mean mu. Now, do you think it's very likely that the true value of the population mean is $382.25? In other words, do you think it's true that the average amount that all SFA students spend on textbooks is that value? That is the X bar value. Really, probably not. It could be the case that the 100 students selected just happen to spend more on textbooks than other students, or less. In fact, the average for all SFA students, the population mean, could be very different from the sample mean of 382.25. Well, the truth is we can't know. No one can ever know no one can ever know with absolute certainty what the population mean is without examining the entire population. Okay. So can we do better than a point estimate? Yes, we can. We can do better than that. So let's look at how we're going to do better. We're going to use what's called an interval estimate. And this is a common thing. If I can motivate it a little bit here, if somebody asks you what's the price of gas at a gas station, at a particular gas station down the road, and you aren't sure what it was, but to give them a pretty confident answer, you might say that it is, between $2.75 and $3.35. So you give them a range of values, and that's a common way of dealing with uncertainty. We give a range of values regarding something we don't know for sure, and that's what a confidence interval does. So this is a new phrase for us. So we move from point estimation to interval estimation. So it's an interval estimate of the parameter where we include how confident we are that the interval contains the parameter we are estimating. So instead of using one point to estimate the parameter, we use a range of values as the estimate. And then we also include how confident we are that the interval contains the parameter. So here's some examples. So playing off the previous examples, suppose we have a 95% confidence interval that the proportion of washers that would fail prior to the expiration date is 10% to 20%. Okay, so here's our interval here. We think that pi lies in here, and we are 95% confident that pi lies in there. This is a pi, by the way. Okay. Example 2, we're 95% confident that the mean waiting time, mu, is between 12 and 15 minutes. Okay. So what do we mean when we say confident? So both of these have 95% confidence. What does that mean? Well, let me first tell you what it doesn't mean. So if we think of the second example, at first glance you might think, well, that statement means that the probability that mu is between 12 and 15 is between is 0.95. So you think of confidence as probability. Well, it turns out that there's a problem with this, because we make probability statements about random quantities. We did that in previous lessons where we made a probability statement about a binomial variable or about a normal variable or about x bar, this sort of thing. Well, in this, under the parentheses here, in that event, there is nothing that's random. There's no, now why do I say that? 12 is clearly not random. 15 is not. Mu, yes, it's a symbol there, but it's a fixed parameter. It doesn't change from sample to sample. And so mu is either between 12 and 15 or it's not. And so to say that the probability mu is between 12 and 15 is 0.95 is erroneous for our interpretation of probability. So this sort of interpretation for confidence is not appropriate. So what do we mean by confident? Alright, so let's think back to, or let's go back with this idea of a 95% confidence interval. That is an interval generated by a process that is correct 95% of the time. So if we were to replicate our study many times and each time report a 95% confidence interval, then 95% of the intervals would contain the parameter of interest. Well, in practice we perform our study only once. We have no way of knowing whether our particular interval contains the parameter. We don't know. If we did know, then we might know our parameter, which is not a common place to be. we just know that 95% of the time our estimation method is correct. Okay, so we have here, I have some charts, some graphs. I have Okay, so revisiting interval estimation, I had begun talking about these two graphs here stacked on top of each other. They're run graphs, and basically what's happening here is we have a population, you can kind of see it in this box here, of a normal distribution is the population, and the population mean is 5 and the standard deviation is 2. So mu is 5, and what's done is a sample of size 50 is randomly drawn from this population, and this is done by a computer, and when the computer draws that sample it computes the sample mean and then it plots it. And so for example, this first sample mean is, looks to be about 5.05. This next sample mean looks to be about 5.1. The next sample mean about 4.9, and so forth. And so you can see the sample means bounce all over the place for the 100 samples of size 50. Some are closer to mu than others, and so what's being done in the second graph below that is the corresponding confidence interval. And here's actually the formula for that. We'll talk about that is the formula is x bar plus a t percentile, we'll talk about that later, times s over root 50, and then x bar minus a t percentile times s over root 50. Again, we'll talk about where those come from later, but that's the interval. And so we're just basically taking x bar and adding and subtracting some stuff to get a lower and upper bound to get an interval. And we're asking the question, again, this is the mean 5 there going across the middle. We're asking the question, did the confidence interval capture the mean mu? Did it capture mu? Alright, and so when we look at the first confidence interval, mu is clearly in there. In the second one, it is as well, and the third one, and so forth. In fact, most of them it did capture mu, but we can see a few where it didn't. Alright, here's one right here, around the 10th sample. Around the 31st sample, we have a point that it did not capture. Around the 52nd sample, around the 76th sample before that, it didn't capture mu, and kind of scanning through here, right there around the 91st sample. So what I had was 5 samples out of 100 samples that generated a confidence interval that did not capture the population mean mu. So this is what we mean when we say confidence, that the method is correct 95% of the time. Okay. Note that an individual interval is computed in practice, and you only have one confidence interval computed in practice, and that's what these examples were about here. And you don't know whether or not your particular interval captured the parameter or not. You're just 95% confident, or say 90% confident, whatever your confidence statement is, that your method is right. And so the confidence statement, confidence level, corresponds to the method that's at hand and not the particular interval that's generated from that particular data set. Okay, so with that in mind, let's continue on here. In practice, we usually construct intervals with the following levels of confidence, usually something like 90%, 95%, 99%. When you start getting below 90%, down to 80%, you can do that. But when you start getting too much below 80%, really below 90%, then you have too many misstatements, and so typically the confidence levels are 90% or higher. But thinking about the confidence levels, there is a trade-off between the amount of confidence we have in an interval and its length. This is the trade-off. The longer the interval, the more likely it is to contain the parameter being estimated. And so you want your interval to be correct. You want it to capture the parameter that's unknown. But in order to do that, for that to be more likely, the interval has to get wider. Okay, so there's this trade-off between the interval being really wide and having a high confidence. Sometimes the interval can be too wide. If it's too wide, then it's not useful. So if I tell you that I'm 95% confident that the price of the average price of gas in a particular town is between 50 cents and $6, that doesn't really tell you very much. I'm probably pretty sure. Actually, I could probably be 99.99% sure that's the case, but it's not a very meaningful interval. 50 cents to I don't know what I said, $6 or whatever. So typically what's done is a 95% level is chosen, 1 out of 20, and so it's almost universally recognized. But we'll see settings where we want a 90% confidence interval or 99% confidence interval. Two things here that are related together: the confidence level and what's called the significance level. The confidence level is denoted as 100 times 1 minus alpha, and alpha is the significance level. The confidence level is the proportion of times your method is correct. The significance level is the proportion of times your method is not correct. And so if we have a 90% confidence, then our alpha is 10%. And really, we're going to, when we go to do some computation, it's going to be 0.10 instead of just the number 10. It's going to be 0.10. And then a 95% confidence level would correspond to an alpha of 5% or 0.05. And if alpha is 0.001, then we're dealing with a 99.9% confidence interval. Okay, so let's look at, actually let me look at an example here to kind of motivate some things. The U.S. Bureau, actually take a moment, read this example here, and so you may want to hit the pause button. In this example, we are wanting to estimate a population mean, right? The average age for all people in the civilian labor force, and that's the parameter we're trying to estimate, mu. This is the parameter of interest. Mu is the parameter of interest. And it is unknown. Okay, so we estimate it with a 95% confidence interval. Alright, so let's go back here, motivating this idea. We want to estimate this parameter with an interval. Alright, here's the method that allows us to look at a confidence interval for mu, the population mean, when sigma is known there. Okay, The conditions or the assumptions that need to be met in order to use this particular interval formula are as follows: that we have a random sample, that we have a normal population, or I'm going to say a large sample. And for us, we're just going to go with the idea that a sample is large if the sample size is 30 or more. We made that designation earlier. You may be thinking in your mind, large sample, what's this from? It's the central limit theorem. So the central limit theorem is going to kick in for us here, and I'll talk more about that later. And then thirdly here, sigma is known. So we've got these three conditions that need to be satisfied in order to use this confidence interval formula. So first we are going to find this thing called z sub alpha over 2. It's a percentile from the standard normal distribution, and you get that from for a given alpha. And so you find that first, and that is step 1, and that's determined by the confidence level of the confidence interval. Then once you have that, you already have x bar. That's the mean from the sample. N is the sample size. Sigma is the standard deviation of the population. This right here, let's see if that'll work. This is the lower bound of my confidence interval. And this right here is the upper bound. Okay. And if you look at the formulas for the lower and upper bounds, they're very similar. They only differ by the plus and the minus sign. So we typically represent a confidence interval formula in this way: x bar plus or minus z percentile times sigma over root n. Now let me say something about this sort of notation here. This formula, let's see if I can try to erase this here. Let's do that. This formula, when you look at the structure of it, that's x bar there, that's the point estimator for mu. So this is our point estimator for mu. Z is a percentile from the standard normal distribution. And sigma over root n, if you recall, that is the standard deviation of my point estimator, sometimes called the standard error of the point estimator. Remember from previous lessons, the standard deviation of x bar was sigma over root n. So if my estimator here is x bar, then sigma over root n here is the standard deviation of the point estimator. This form, a point estimate plus or minus a percentile times a standard error, is going to be a very common form for us in computing confidence intervals. Okay, so let's get back to this example here, estimating the average age. So we're going to use the formula